So the first term we're going to review is the contact. And what a geologic contact is, you might recall this from the mapping exercise. It's just a surface where two geologic rock formations touch. So on a geologic map, this is a simple line. What we're going to be talking about today are cross sections. And so if I draw a geologic cross section on this page, let's see how my drawing skills work here. What contacts are, that is horribly uneven, but what contacts are simply these lines. Yeah, so what we're looking at here is a pie slice of the Earth's surface. Those lines are geologic contacts, areas or surfaces where rock type 1 meets rock type 2. So here is a formal definition you can write down. The surface where two rock layers touch, and this can be a line on a two-dimensional map. And your diagram for this can simply be what I just drew. Some lines, and then you can draw an arrow to one of them, and that would be a contact. Nailed it. Okay. Pause it here if you need to write this stuff down. Otherwise, I'm going to be moving on. Term number 2 is original horizontality. These geologic laws and principles are not difficult. Very, very not difficult, so please don't overthink them. We're going to be talking about, especially in Central Texas, sedimentary rock geology. So this type of rock is deposited through the lithification of sediments. It takes place, as we've discussed, on ocean floors. So sediments, whether they be dead parts of organisms, other sort of particles in the ocean, descend to the bottom of the ocean and are lithified into rock through the combination of pressure and the atmosphere down there. As you probably might assume, these rocks are always deposited horizontally. And so one of the major laws of sedimentary rock geology is this law of, quote, original horizontality. What this says is that rock layers, especially sedimentary layers, tend to be deposited in relatively horizontal layers. So if we're drawing a diagram of this, we'd pretty much draw the exact same diagram. Sorry, I know these are kind of boring thus far. And you can say that, okay, these layers are deposited horizontally. That is the law of original horizontality. So if you see in the rock layer or in the rock record something that's not horizontal, either that's not sedimentary rock or something has happened to that sedimentary rock since it was deposited. Feel free to pause it here. Raise your hand if you need the sub to stop this video clip so that you can write stuff down. Okay, so the next geologic law we're going to be talking about is superposition. This one's just as simple. Here is the definition. So this is basically stating superposition, that in sedimentary rock layers, the oldest layers are on the bottom, the youngest layers are on the top. Pretty simple. So if I'm drawing this out, I'd have originally horizontal rock layers. Here they are. And if I draw a bunch of layers, I know that my oldest layers are down here and my youngest layers are up here. So if I'm numbering these, oldest 1, 2, 3, 4, and 5 would be the youngest. Superposition. It's a law of superposition. It's not complicated. Pause here if you need to write stuff down. This is all I had for the diagram. It's not very intricate at all. So the next concept that I will need to review is the concept of the unconformity. And what an unconformity is it's really representative of an erosional surface that represents missing geologic time or a gap in the geologic record. So I will try to symbolize this. Here's a definition. So unconformity, old erosional surface, gap in geologic history. Let's talk about what that means. And here I think that really the graphical explanation is much better than the textual one. So let's say we have horizontally deposited sedimentary rock layers at the bottom of an ocean. Here we go. And remember, rock layers are deposited when the sea is above a particular landscape. let's say for some reason the sea drops below that particular landscape. So we have layers 1, 2, 3, and 4 here. Let's say the sea drops below the particular landscape and exposes this rock to erosion. I'm going to use the eraser to erode off some of these layers. So we're eroding over a long amount of time through layer 4, through layer 3, lots of erosion, through part of layer 2. How unconformities are symbolized on cross-sectional diagrams is by squiggled lines. So what I would draw on the top here would be a squiggled line, and that represents an erosional surface. Let's say at this point, seas rise again, and the area is dominated by deposition processes. So we then get deposition of other layers on top. Now if you recall, the layers that were eroded, they were 3 and 4. This represents that erosion surface. So if I'm drawing this out in reference to the drawing that I had before, I would not draw 3 and 4 again. I would make this layer 5, 6, 7, and 8. So that's where this gap comes in, right? This is an erosional surface that really represents a gap in the geologic record. If we were to take isotopic data from here, radiometric data, isotopic data here, radiometric data, we would distinctly notice that this is discontinuous and that that's a gap in the geologic record, and that's because erosion has happened and really erased that rock from existence, at least in this cross-section. So an unconformity, an old erosional surface, a gap in geologic history. So a disconformity is a specific type of unconformity. So you can really categorize this under unconformity. What a disconformity is the exact type of unconformity we just drew. So you can leave that drawing in your on your page. But a disconformity is an unconformity between parallel layers of sedimentary rocks representing a period of erosion. So you might notice in the one that we just drew, I'll redraw kind of a version of it here. Let's say this is 1 and 2, and this is 4, 5, and 6. We're missing layer 3. That would be a disconformity. It is an unconformity, but at the more specific terminology, it's a disconformity because this deposition and this deposition, those are parallel in relation to each other. Disconformity. So take a second, pause this if you need to write down that definition, but really we're talking with a disconformity about parallel layers of sedimentary rock separated by a period of erosion. An angular unconformity is a slightly more difficult concept, and an unconformity where horizontally parallel strata of sedimentary rock are deposited on tilted and eroded layers, producing an angular discordance with the overlying horizontal layers. Now that's the definition from the textbook. Don't feel the need to write that down verbatim. I'd rather you, at this point, pay close attention to the diagram that I'm about to draw because I think that helps this make a lot more sense. So let's say, start us off, we have horizontally deposited rock at the bottom of an ocean. 4 layers, 1, 2, 3, and 4. Let's say some tectonic event happens. We don't have to know specifically what it was, but that tectonic event serves to compress these layers, and we get a fold in the geologic record. So I'm going to delete this and redraw it after that event happens. There's 1 layer, 2 layers, 3 layers, and my 4th one's down here. So 1, 2, 3, and 4. Okay, so that's what it looks like after this fold has occurred. Let's say at this point, seas recede, we expose this landscape to erosion. So what would that look like? We have erosion knocking off the top of this guy or girl. Okay, and so if I wanted to redraw my layers, I'd have to symbolize 3 over there and 4 there. How do I symbolize a surface of erosion? With squiggled lines, like that. And let's say the seas rise again, and I get deposition. Now that deposition would be horizontal, and it would be horizontal on top of this. So that this would be 5, this would be 6, this would be 7. What an angular unconformity is that. Notice that the layers down here are not parallel to these layers. So this is an unconformity where horizontally parallel strata, these, are deposited on tilted and eroded layers, those producing an angular discordance, that, with the overlying horizontal layers. That's what an angular unconformity is. So really, if you're looking at one thing down here and it's tilted or crazy or weird, and the other thing on the top is parallel, that's an angular unconformity, as long as there's an erosional surface, this guy, in between them. This typically represents larger gaps in geologic time when you're looking at the rock record, because if you notice, going from here to here, we're going from layer 2 to layer 5, so we have a larger gap there, and that typically is associated with the fact that a tectonic event has happened between the deposition of this and the deposition of that. That's an angular unconformity. Again, if you need to pause this and write stuff down, go ahead and do that. So the last principle that I need to talk to you about is that of cross-cutting relationships. This is extremely straightforward, just like all these. Let's say we have a horizontally deposited sedimentary cross-section. Cool. Layers 1, 2, 3, 4, and 5. Okay, let's say at this point we have some igneous activity boiling up from the bottom that cross-cuts this entire rock record. And I'll symbolize that igneous rock by little stars. Typically not much organization in igneous rock, so there we go. That's the igneous cross-cut. We can call that an igneous intrusion. What the principle of cross-cutting relationships suggests, very simple, is that this igneous intrusion is younger than the rock that it cross-cutted. Pretty dang straightforward. Where this gets complicated is, I'll draw a diagram out on the next slide and show you where it gets a little bit more complicated. So here's a formal definition of this. Geologic features, and on the previous slide I gave you the example of the igneous intrusion, but this can also happen with faults, with river crosscuts, whatever. Those features are younger than the rock layers they cut across. Let me show you where this gets slightly more difficult, although not that difficult. Let's say I have a similar situation to what I just drew previously. I have some rock. I then have an igneous crosscut coming right up through it. Cool, there's my igneous crosscut. Let's say I have erosion knocking off some of this top. Cool. To symbolize that erosion, I would draw a squiggly line. And then let's say on top of that, I have originally horizontal deposited bedrock. So, what we can note is that the igneous intrusion, let's say this is layer 1, 2, and 3, and we erased layer 4, so let's say this is layer 5, 6, and 7. The igneous intrusion would be younger than layer 3, but older than layer 5, because note that it does not cross-cut layer 5. So it gets slightly more complicated, but as long as you're analyzing what layers it's cross-cutting and what layers it's not, it's pretty simple.